By the end of this video, you'll be able to solve through the classical wave equation on your own, which will set you up really great for solving the particle in a box wave functions from the Hamiltonian. So let's solve for u of x of t. The one major assumption that we make is that the displacement in the x direction and the displacement in the t direction, or the time, are going to be independent of each other. So this is one major assumption where we use separation of variables, where u of x of t can be separated into a displacement in the x direction and a displacement in the t direction, where they are independent of each other, so we can separate them into a function of x times a function of t. This will make it so we can actually solve this differential equation above. So let's plug in our x and our t function into u. We will factor out the function that does not matter. So here we have our second derivative, partial derivative with respect to x of x and t is equal to 1 over v squared, with the second partial of respect to t of x and t. For those of you that are curious, this velocity talks about the speed of the disturbance of the string, so different disturbances of this amplitude that might be changing. And it'll be more important later on when we combine it into a constant. So now, what we can actually do is that since we have partials with respect to x and t, and now these functions are actually separable, what we can do is factor out the functions that do not have those specific variables. So like on the left here, we're taking a partial with respect to x, so this t function can now be factored out, and now this becomes a regular derivative, or regular second derivative, with respect to x of our x function. And it's equal to, we factor out our x function, all over v squared, and we take our second derivative with respect to t of our t function. Now this is when we can actually do some separation of variables, and we can bring all the x's on one side, all the functions of t on the other side. Let's bring our x functions on the left and our t functions on our right. We will get 1 all over x with the second derivative with respect to x of our x function is going to be equal to 1 all over t times the velocity squared with our second derivative with respect to our t function. Now there's something special about this, where this is saying that for any values of x and t, these are always going to be equal. And the way that they're always going to be equal, if they are equal to a constant. So this is the second thing that with some math knowledge, and maybe you just have to memorize this, that once you separate a function with respect to x is always equal to a function with respect to t, it always has to be equal to a constant. And I'm going to write that as constant is equal to c. Because of this, we can actually solve for these individual equations separately. So we'll have a spatial part of our disturbance, and we'll have a temporal part of disturbance that we'll both solve individually. So first, we're going to look at our spatial part of our disturbance because we also have our boundary conditions. Whenever x is equal to 0, our displacement will be equal to 0, and when our x function is equal to a, or x is equal to a, our x function will be equal to 0 as well. So we're going to be looking at the function 1 all over our disturbance, d squared all over dx squared of our x function is going to be equal to our constant c. And we're going to solve for this equation for 3 different cases, because this constant can either be positive, 0, or negative, and we'll get different varying results. These 3 cases will result in 3 different solutions, where only one of them will make physical sense. So let's attempt some. Let's do the first case where c is equal to 0. So this equation will be 1 over x multiplied by the second derivative with respect to x is equal to 0. And so when we can solve for this function, so what we can do to solve for this function is multiply both sides by our function of x. So now we'll get the second derivative of our x function is equal to 0 times x, so it is just 0. An easy way to solve for this differential equation is to separate our variables. We'll have our d squared of our x function is equal to 0 times dx squared. And this also means that we have two integrals that we have to take in order to solve for this, dx. So if we take our two integrals where we have 0 as our constant, what we end up seeing is that after our first integral, we will have that we have a constant, so let's call this b, because the derivative of a constant b is always equal to 0. So now if we take the second derivative now, or second integral, sorry, we'll take the integral and we'll see that our x function is going to be equal to bx plus another constant c, or let's call it a in this case because we already have c. So our solutions for our functions of x is actually a polynomial or a linear polynomial of bx plus a, where b and a are constants. So let's see if this result is actually physically viable when we plug in our boundary conditions. And since we already have c as one of our constants, let's say this constant is now d. Now we have to plug in our boundary conditions to see if this function actually makes sense. So we have whenever x is equal to 0, our function is equal to 0, right? So let's plug in 0 for x. So when x of 0, b times 0 becomes 0, so we have is equal to d, and we know this result is equal to 0, so we know d is equal to 0. So now we know bx is the only term we have left, so let's see if that makes sense. So whenever x is equal to a, our function of x is equal to 0. So x of a now is equal to b times a, which is equal to 0. The only way this is equal to 0 if b is equal to 0 or a is equal to 0, and we know a is to be greater than 0 from our box definition. So b has to be 0. And so the only function that satisfies whenever our case 1, where our constant is equal to 0, is that our whole function of x is equal to 0. So this is trivial. So this is not our solution. So case 1 does not work for our solutions. So let's move to a different case. Let's look at when our case, whenever we have c is equal to k squared, and any value squared is always going to be positive. So this means c is positive. Keep that in mind. So now we have our original function, 1 over our function of x times the second derivative with respect to x of our x function is equal to k squared, is equal to a positive value. So if now we solve for this second derivative, if we solve for this function, we'll multiply our x function on both sides. We'll get our second derivative of our x function is equal to k squared times our x function. And now we set it equal to 0 by subtracting our right function minus k squared is equal to 0. Now we have to solve for a solution here. And an easy way to solve for this solution is that when we have a homogeneous where it's equal to 0, and we have something like a second derivative here, is that we have we do a trial function where x, our function of x, is equal to e alpha x. And we're going to be trying to solve for alpha here. So if we plug in e to the alpha x, we'll see that our second derivative of e to the alpha x minus k squared e to the alpha x is equal to 0. When we actually solve for this, we'll see that alpha squared comes out in front because two derivatives of e to the alpha x times our original function minus k squared e to the alpha x is equal to 0. And now in order to solve for alpha, we know e to the alpha x is never going to be negative. So we can divide by e to the alpha x on both sides, and that'll be physically acceptable. This will result in alpha squared minus k squared is equal to 0. And so when we solve for alpha, we'll get alpha squared is equal to k squared, and alpha is equal to plus or minus k. And this means our solution of our function of x can be either e to the kx or e to the negative kx. The important part of quantum mechanics and linear algebra, this is where it's based off of, is if we have two solutions for our equation, our solution actually can be any combination of these solutions with different constants. So let's say it could equal c1 times e to the kx plus c2 e to the minus kx. So we actually have to look at the combination of the two solutions, not just the two solutions individually. So this is our general solution, but now we have to plug in our boundary conditions to see if these solutions are trivial or not. So when we plug in 0, we'll get x of 0 is equal to 0. And when we plug in 0 for both our x's, our e terms will become 1. So we get c1 plus c2. Now if we look at our x is equal to a is equal to 0, we can see that our functions are now c1 e to the ax plus c2 e to the minus ax. And we know from above that c1 plus c2 is equal to 0, so this is also saying that c2 is equal to negative c1. So if we plug that in for c2, we'll see that we have c1 times e to the ka plus c2, or sorry, minus c1 e to the negative ka. We can factor out our c1s, and we'll see that we have e to the ka minus e to the negative ka. And I'm not going to go into the full explanation of this, but if you end up plotting this function here on the right, where k is never going to be equal to 0, we'll see, or since we know k is not going to be equal to 0 because we have a positive value, this term will never equal 0. So we know the only way that this makes it 0 is that c1 has to be equal to 0, and so c2 also has to be equal to 0. So this is another trivial solution as well. So now we have to go to our third and final case to actually solve for our spatial parts of our wave function, where our constants for our separations of our temporal and spatial parts of our wave functions are actually going to be negative, or we have a negative k-square because this will always result in a negative value. So we'll have 1 over our x function multiplied by the second derivative of our x function to be equal to our negative value here. If we solve like before, dx squared of our x function will actually be plus k squared x of x is equal to 0 after you solve around for it. Now again, we're going to do our trial wave function here, where x is going to be e to the alpha x because we have our 0 or is equal to a constant of 0. This just makes it easy because our exponential functions will never equal 0, so we can divide by them in the end. So we'll have the same result here. We'll get alpha squared plus k squared this time, multiplied by e to the alpha x is equal to 0. And so we get alpha squared plus k squared is equal to 0. So alpha is actually to be equal to, alpha squared is going to be equal to negative k squared. And when you take the square root of that, it's actually going to be plus or minus I k. This is going to be important because this imaginary term actually makes it so this will actually oscillate with Euler's formula. So when we plug this in, we'll see that x e to the ikx or e to the minus ikx. And again, we have to take both solutions into account when we solve for this. Plus c2 e to the negative ikx. And using Euler's formula, this is going to be important to actually use to solve for this, where e to the I theta, or any term after our I, is going to be equal to cosine of theta plus I sine of theta. So using this, we can actually solve for our function. So we'll get x of x is going to be equal to c1 multiplied by cosine of kx plus I sine of kx plus c2, which is to be cosine of kx minus I sine of kx. The reason why the cosine is positive because it's an even function, so if you take a cosine of a negative value, it's just the same thing as taking the cosine of the positive value without changing the sign. But the sine function is off, so that's why we have to flip the sign whenever you apply it onto our negative value in the parentheses. So I'll write that down here below. If it's e to the negative I theta, we'll get cosine of theta minus I sine of theta. So now when you combine like terms, we're going to get C1 cosine of kx plus C1I sine of kx plus C2 cosine of kx minus C2I sine of kx. And we can redefine a lot of these constants in front of our values. So we factor out everything that has a cosine term. We'll have C1 plus C2 times cosine of kx plus I C1 minus C2 sine of kx. We can redefine all these constants in front of our sine and cosine terms, and we'll just call this A cosine kx plus B sine kx. You don't need to retain the I or anything. The I is a constant, just keep that in mind. So now we can redefine it as A and B in front of our cosine and sine terms, which makes this very easy, right? So this is the general solution, but now we have to apply our boundary conditions, like before, where if x is equal to 0, our function is equal to 0. So if we apply that, we will get A times cosine of 0 plus B sine of 0. And cosine of 0 is 1, while sine of 0 is 0. So we'll get that this whole function is equal to 0, and the only term that will remain is A. So we know A is equal to 0. So our cosine term doesn't remain. If we do this for x is equal to A is equal to 0, we will have that x is equal to A, and our cosine term is gone, so we have B sine of k times A. Now this is very important because if B is equal to 0, then we'll have another trivial solution and nothing will actually end up working out. But sine does equal 0 whenever we take the sine of pi times an integer n, where n can be 1, 2, 3, all the way to infinity. So what we can say is that this function will actually be equal to 0 if our inside of our sine terms is also equal to n pi, which is very useful, right? Since we have a k that's defined in our sine term, if we want to define it further, we can say k is just equal to n pi divided by our length of our blocks. So if we apply that into our definition of our general solution, we'll see that our function of x term is equal to our constant b times our sine term, where k times x is now going to be n pi x all over a. N pi x all over a. And this is our spatial solution for our classical wave equation, for our displacement. And by the way, if I ever say wave function during this, technically it's not a wave function because we're not dealing with quantum mechanics yet, but this is for the classical wave equation, so I might call it a wave function for this video. But this is how you solve the spatial part of that solution. And we will actually use this definition of k in our next problem because we know our temporal part is also equal to k, right? But we have half of our solution. All right, so now that we know the spatial part of the wave function, we just have to remember that our disturbance with respect to x and t is equal to our spatial part, which is just what we solved for, times our temporal part, our time function. So we solved for our spatial portion of our disturbance function. Now we're going to be solving for our temporal function here. When we go back to what our specific derivation was in a separation of variables, we have 1 all over t of t multiplied by our velocity of our disturbance squared, multiplied by the second derivative with respect to t of our temporal function. And this is equal to our negative k squared. Now again, we have to remember we have to use our negative sign because just like before, the three cases, only the negative constant will result in any meaningful answers. So when we're going to multiply both sides by our t function and our velocity squared, we'll get d over dt squared, t of t is equal to negative k squared v squared times our t function. And then this whole thing will equal 0. Plus k squared v squared t of t. And then if we do the same trick as before, but now our trial function is going to be e to the alpha t, because t is our variable in this case, not x. When we're solving for that, if we plug it in, take the derivatives, if we take the second derivative, we'll get alpha squared plus k squared v squared multiplied by our trial function. And remember, our trial function is never going to be 0, so we can divide by both sides by that. And so we get alpha squared plus k squared v squared is equal to 0. And we'll get alpha is going to be equal to plus or minus I k v. This is known as this is going to be the coefficient in front of our t for our trial wave function. And again, since we have two solutions, this means that we're going to have a linear combination of these two solutions, where we have c1 times e to the I k v t plus c2 e to the I negative I k v t. And something for a little bit of a notation, as we know, for the last problem, k is equal to n pi all over a. And here we have n pi v over a. This is going to be equal to what is known as omega n, or the angular frequency of vibration. So if we plug that in, we'll see that our temporal function is equal to c1 e to the I omega t. And we can say omega nt because this is depending on n, plus c2 e to the negative I omega nt. And just like before, if we plug this in with our Euler formula, we'll see that we'll end up getting, and I'm going to end up rearranging and calling them new constants. And I'm going to use the constants just plain c and d. We have c times cosine of omega nt plus d e to the sine of omega n t. And to be more exact in this case, our omega is depending on n, right? And so our constants should also as well. So it should be constants with respect to n. So these might change depending on what mode we're using, what normal mode we might be using, which is what we're solving for here. And this is the exact solution for our temporal part of our wave function. So now if we combine the two, we know our x function, or spatial function, is equal to our amplitude, or a constant, times sine of n pi x all over a. And we know our temporal function is equal to this constant sine cosine omega nt plus our constant with respect to n sine omega nt. And now our actual disturbance function, and this is also corresponding to our wave function that we'll end up using for quantum mechanics later on when we actually have a better model system to talk about. And before we actually combine these two functions, as we know, our disturbance function is equal to our spatial times our temporal functions. What we can remember from trigonometry is when we have a sine plus a cosine term, what we can actually write this as is one singular trig identity, where we'll make a new constant here. We'll have g of n is times cosine of omega n t plus a phase term phi of n. This is the same formula as this before, as the ratio between our c of n and d of n. will give us our phases of r, will give us the phase term of phi of n within our cosine term here. When we combine these two functions, this will be a solution that depends on n, where n is our normal mode with this case. So we can have our first normal mode, second normal mode, third mode, fourth mode, and this will end up being a function that depends on n with our spatial part and our temporal part. And so this is one solution, but as we remember from before, the most accurate solution that describes the whole function of wave disturbance is equal to the sum of all of these solutions from n to infinity, or n to n in this case, if we're just counting for a certain amount of normal modes, which is just also equal to n1 going to n of f of n sine n pi x all over a cosine omega n t plus phi of n. This is our actual solution for our vibrating string. We can make a lot of relationships to like a guitar with fixed boundary additions where it just vibrates and oscillates between each point. This will be very important as many of these techniques will relate to quantum mechanics, especially with the solutions of the particle in the box, which we'll talk about in a future episode. But I hope you have learned something today, and please support my channel and have a great day.